All right, let's take a look. So here is the region bounded by x squared plus 1, y equals 0, x equals 0, and x equals 1. We're supposed to revolve this region around the line x equals 2, so spin it around like so. So let's see if I can draw the reflection here. Okay. There we go. Okay, I'm going to think through, do I want to go with a dx or a dy? In this case, a dx integral, remember that means your rectangles are perpendicular to the x-axis. A dx integral in this case would mean the cylindrical shell method, and a dy integral would mean the washer method, okay? Now, if I stick with the washer method, first of all, I think that dy integrals are less fun than dx, so that's reason number one to not go washer method for me personally. And then reason number two to not go washer method is because this looks like either a two integral approach or a geometry plus calculus approach. And I'd just rather do one integral and get it done. Okay, so for those reasons, I'm going to stick with the cylindrical shell method. Okay, so here's my dx rectangle. And then actually maybe I should draw it. No, that's fine. I'll draw it a little further in. Okay, here's a dx rectangle. And then let's draw its little trip as it gets revolved around. Like so, okay? So let's set it up. So I'm just gonna write the words out first. So 2 pi integral from a to b, radius of my cylindrical shell times height, and then d, and in this case we are going dx, so I'll just write that in, okay? So what should I put for radius? And this is where it can get a little bit tricky, okay? Some people think, especially after the first couple, that your radius will always be x, but you have to look at your original picture to decide that. Well, what is your x coordinate, like, to get onto this function, right? Like, your x coordinate is this distance. My friends, that's what x is. So is that the radius of my cylinder? Absolutely not. So a couple questions. So I'm going to ask you, what's the distance from my axis of revolution all the way to the y-axis? The answer is 2. So this whole distance from here to here is 2. What's this distance? Say x. It's x. So what's this distance? Well, it would be 2, take away x. So my radius here is actually 2 minus x. In this case, I hope that makes sense. This is a strategy that can apply to all sorts of problems I'm sure you've encountered in your homework along the way. Okay, now let's look at the height. What is the height of this region? And it's basically just your y-coordinate that it takes to get up to the graph. No need to add or subtract anything to it. And so your height would be your y-coordinate, written in terms of x, of course, because it's supposed to be a dx integral. Like that, okay? What should my a and b values be? Well, we would go from 0 to 1. Now, some people wonder, how come you're not also using these numbers over here? Here's the reason. When you do 0 to 1, your integral will slowly accumulate the rings that were created by revolving all the little rectangles from 0 to 1 around 360 degrees. So all the little rectangles that are formed from 0 to 1 create the entire thing. If you did this stuff as well, then you'd get double your answer. Okay, so your volume then would be set up as 2 pi times the integral from 0 to 1 of the quantity 2 minus x multiplied by the quantity x squared plus 1 with respect to x. All right, and now I'm just going to punch this into my calculator. Okay, keep in mind that that is just the integral part, so I'm going to multiply it by 2. Okay, notice the exactly equal to symbol because I did get this repeating decimal. And so units cubed, and then I'll just go ahead and multiply by pi as well. There we go. I have my answer written in terms of pi, whoops, and then in pure decimal form. There we go. Hopefully that makes sense, my friends. So let's, at this point, let's just finish this lesson by doing a quick summary of formulas that after the first two lessons in chapter 6 you should be familiar with, okay? There is the idea of the area of a region bounded between two functions. Okay, there is, we'll go back and fill them in just a second. There is volume of a solid with a known cross-section. There is the washer method. And there is the cylindrical shells method. There we go. Okay. So let's see, area of a region bounded between two functions. Well, I suppose it depends, right? So if you have a function of x, you know, and then another function of x, and you're trying to find, you know, the area of the bounded region on a given interval, then if you're given functions of x, then it would be upper minus lower. So the integral from a to b, and we're just going to write the words down. And then that's if it's a dx situation. But if you're given functions, things that aren't functions of x, right? Like you can see they fail the vertical line test, right? In which case they are, as long as they pass the horizontal line test, they would be functions of y. Right? If you're trying to find the area of the bounded region of something like that, then in that case you would do instead of upper minus lower, you would do right minus left. In both cases, it's kind of taking the function that's more positive and subtracting off the function that's less positive, whether you're doing upper minus lower or right minus left. Anyway, so in this case, you could say or the integral from a to b of right minus left, and then that would be if you're doing a dy type deal. Okay. So volume of a solid with a known cross-section. So that was where you had, you know, you have a region as a base, whatever, and you have some known cross-section coming up, like maybe equilateral triangles, you know, or something like that. And you had that, I don't know. This is horrible. Anyway, pretend that looks amazing. Anyway, so you have this volume with known cross-sections. The trick there is just figure out the area of the cross-section and then pop that into an appropriate integral. So you would say volume could equal the integral, I'll just kind of draw, from a to b of appropriate area function with respect to x, or remember, sometimes you could have cross-sections that are perpendicular to the y-axis, and that would be very similar, just you'd get everything in terms of y. So there you go, okay? Okay. Funny story, the washer method is really just a special case of the volume of a solid with a known cross-section. It's just that the area function we're using is the volume of a washer, no big deal. And then there's also the disk method where your inner radius is basically 0, and you're just adding up a bunch of circles. So the washer method is really just a drill and kill of a special case of area of a known cross-section. If you really think about that, you might have a little breakthrough there if you've needed one. So the washer method depends, again, on what you are integrating with respect to, but I'm just going to write this one in words so we don't have to write too much. So pi times the integral from appropriate bound to appropriate bound, and then of inner radius squared, take away outer radius squared, and then with respect to appropriate variable, x or y, depending, okay? All right, cylindrical shells method, that should be the freshest in your mind. So that one is 2 pi times the integral from a to b of the radius times the height, both of your cylinder, that is, and then with respect to appropriate variable, okay? All right, if you've managed to get this far and still haven't memorized those, I highly recommend you do for your sake and happiness in this class. Anyway, hopefully things are going well. Feel free to email me or ask me questions in Zoom. Either way, I'm always happy to help. Take care, everybody.